Hello everyone, and welcome back. Today we're going to be continuing our exploration of foundational proving principles and focus on a method known as mathematical induction. We will not be proving the theorem for mathematical induction, but we're going to be using mathematical induction sort of as an axiom to sort of show how we can prove other things from it, and we'll leave the proof for the mathematical induction theorem for a later time. So what exactly is mathematical induction? So what we're going to do is we're going to let S be the subset of natural numbers that satisfy two properties. The first property is that 1 must be an element of the set, and if we assume that for some arbitrary k in the set of natural numbers that belongs to the set, if that implies that k plus 1 is also an element of the set, in addition to 1 being an element of the set S, then this mathematical induction principle, which some people just abbreviate as MIP, implies that S and N, the set of natural numbers, are identical to one another. That is, if you can prove 1, that 1 is an element of the set S, and 2, k and S implies that k plus 1 is an element of S, that means whatever property that this set S substantiates in terms of, what works and what doesn't work, is true indeed for the set of the whole natural numbers. So what I want to do is sort of illustrate this with an example that you've probably already seen up to this point. And that is the sum of consecutive natural numbers. So if you have 1 plus 2 plus 3 plus 4 all the way up to n, one can actually show that this is indeed equal to n times n plus 1 divided by 2. So is this really true for all natural numbers n? So that's the question that we want to know. So is this true for all n in the set of positive natural numbers? So let's just try a couple examples. For example, n is equal to 3. So when n is equal to 3, what do we have? So we have 1 plus 2 plus 3, right? So that's obviously equal to 6. So we want to know, is this equal to 3 times 3 plus 1 divided by 2? Well, that's just going to be 3 times 4 divided by 2, which is 12 divided by 2, which is equal to 6. So it's obviously true because 6 is equal to 6. Let's try a couple other numbers. For example, n is equal to 5. So when n is equal to 5, what do we have? So we have 1 plus 2 plus 3 plus 4 plus 5. So we have 1 plus 2 is 3 plus 3 is 6 plus 4 is 10 plus 5 is 15. So we have 15 on the left-hand side. So is this really equal to 5 times 5 plus 1 divided by 2? So what is that equal to? Well, that's just 5 times 6 divided by 2, which is 30 divided by 2, which is equal to 15. So it works for n is equal to 3. It works for n is equal to 5. So does that directly imply that it's true for all n? No. And that's very, very important. So just because it is true for some set S, a subset of M, this does not necessarily imply that this is true for all n in the set of natural numbers. This is very important. In particular, you can't prove by example. You have to, in some sense, prove for all. Right? So let's see if we can use the mathematical induction principle to sort of prove this. So keep in mind, the mathematical induction principle mandates that first, 1, the initial step, belongs to the set of values that work. Then we're going to assume that for an arbitrary k it works, and see if that implies that k plus 1 works. So let's try the first step. So is this true for n is equal to 1? So is 1 belonging to the set S? So 1 obviously is equal to 1. Is this equal to 1 times 1 plus 1 divided by 2? So that's obviously equal to 1 times 2 divided by 2, which is equal to 1, so that is true. So this implies that 1 belongs to the set of values for which this identity works. Now let's see if it indeed works for any natural number n. All right, so let's formally state this theorem that we're trying to prove here. So we're trying to prove that the sum from k is equal to n of k, i.e. 1 plus 2 plus 3 up to n, this is indeed equal to n times n plus 1 divided by 2 for all n in the set of natural numbers. All right, so let's formally set up this proof. So proof. So what we're going to do is we're going to let S be the set of all natural numbers such that the above identity is true. So the above identity is true. So, firstly, we need to show that 1 is an element of S. We've already shown this to be true, so we do not need to show it, but if you want to be formal, you can sort of state that here. So the second thing we need to do is we need to assume for some n in the set of natural numbers, so we're going to pick an arbitrary number n in S. That is, we're assuming that the sum from k is equal to 1 to n of k is equal to n times n plus 1 over 2, and we need to show that does this, so does n belonging to S imply that n plus 1 also is an element of S? And if so, that means S and the set of natural numbers for which this is true are indeed identical to one another. Right? So what is our assumption? So our assumption, i.e. step 2 of our little 3-step process, is that 1 plus 2 plus 3 up to m is equal to n times m plus 1 divided by 2. So let's see if this implies the next step. So what I'm going to do is I'm going to take this left hand of the assumption and I'm going to add m plus 1 to it, and I'm going to add m plus 1 to the right hand side of this. Because if left is equal to right, that means L plus something is equal to R plus something. So that means 1 plus 2 plus 3 up to n plus some number is equal to n times n plus 1 over 2 plus that same number. So in some sense, I'm just adding 0 to one side of the equation, and I'm just rearranging this equation. So obviously the identity we have on the left-hand side is the sum from k is equal to 1 to m plus 1 of k, and we need to show that this is equal to n plus 1 times n plus 1 plus 1 divided by 2. So what do we get? So I'm going to get a common denominator for these two fractions. So it's going to give me n times n plus 1 divided by 2 plus m plus 1. And I'm going to multiply top and bottom by 2. And that's just going to give us n squared plus n once I distribute that first out. And then we're going to have 2m plus 2 all over 2. So once I combine like terms on the top, I'm going to have n squared plus 3n plus 2 all over 2, which is a quadratic equation which actually factors quite nicely. So it's going to be equal to n. So what two numbers multiply together to give you 2 and add together to give you 3? That's obviously going to be 1 and 2. Right? So what I'm going to do is I'm actually going to write this as m plus 1 times m plus 1 plus 1. Right? And I'm going to write that over 2. And I'm going to use a u substitution to make this a little bit more obvious. So what we have is this is u times u plus 1 all over 2, and the left-hand side is that this is equal to the sum from k is equal to 1 to u of k, right? Which is the identity for which we have. So the only thing that we assumed in this process was that n belonged to the set S, and we showed from here that, and this should be u by the way, that u also is an element of S, which is equivalent to saying that m plus 1 is an element of S. So since we showed, firstly, that 1 is an element of S, and that n belonging to S implied that m plus 1 belonged to S, that means that S and n are identical sets, which means that this identity is true for all natural numbers n. The mathematical induction principle can work on other theorems aside from inequality theorems. For example, it can also work on divisibility statements and theorems as well. For example, suppose we have the statement 5 to the power of 2n minus 1. Our goal is to prove that this object is divisible by 8 for all natural numbers n. So if you want to try this proof out on your own, feel free to pause the video and try it out for yourself. So let's start off by defining our set of values that this indeed works. So we're going to let S be the set of all n such that 5 to the 2n minus 1 is divisible by 8. Right? So the first thing that we need to show is that 1 belongs to our set. So does 1 belong to our set S? So what do we have? So we have 5 to the 2 times 1 minus 1, which is the same as 5 squared minus 1, which is the same as 25 minus 1, which is equal to 24. So is 24 divisible by 8, yes or no? So as long as you can find some integer k, some k instead of integers, such that 8 times k is equal to 24, then you have proof by definition that this number is divisible by 8. So in particular, we know that if k is equal to 3, because obviously 3 is an integer, we have that 24 is equal to 8 times some other integer, and in this case is 3. So if that is the case, that means 1 belongs to our set. So now what we're going to do is we're going to assume 8 divides 5 to the 2m minus 1 for some n in the set of natural numbers, i.e. we're assuming that m belongs to our set S, and we're going to see if n plus 1 divides that general form as well. So what do we mean exactly when we assume that 8 divides that particular object? So that means that there exists some integer, k, such that 5 to the 2m minus 1 can be represented as the product of 8 times that integer, right? So we're assuming that there exists an integer k such that this is true. That's what we mean by 8 divides that number, right? So let's go into our fun step. This is usually the more harder part, to sort of see if this implies the general case. So is 5 to the 2 m plus 1 minus 1 also divisible by 8? If so, that means m plus 1 belongs to our set, and we're done. So let's start off by distributing this little exponent. So this is going to be equal to 5 to the 2n plus 2 minus 1. And I'm going to write this by using our properties of exponents. So that's going to be equal to 5 to the 2n times 5 to the 2 minus 1. So notice what we have here. We almost have our 5 to the 2n minus 1, but this little 5 squared thing is kind of annoying. So usually when we have this type of structure is usually when you have to add some clever form of 0 to sort of factor that annoyance out of your expression, so you're just left with the two things that you want in your linear combination. So the common one is that you add and subtract the thing that you're trying to get rid of. So in this case, I'm going to subtract, so let's not forget our 5 squared. So 5 squared, I'm going to subtract off 5 squared, I'm going to add 5 squared, and don't forget g or minus 1, right? So that is my plus 0, and I'm putting my minus first because I want my 5 to the 2 and minus 1 to be present in my first term, and I'm just crossing my fingers that at the end turns out to be something nice that I can deal with, but we'll see once we get to it. So for the first two terms, I can factor out our 5 squared, so I'm going to be left with 5 to the 2n minus 1. And then over here we have 5 squared minus 1 that we can group together. Keep in mind, 5 to the 2n minus 1 is already expressed by our induction step as just 8k for some integer k. So we can write this as 5 squared times 8k plus 5 squared, which is 25 minus 1, which is going to be 24. Right? So once we have that, well, 24 we know is divisible by 8 as well, because we can write that as 8k plus 8 times 3. And notice that we have an 8 in common with the first and second terms. So if that's the case, I can factor out my 8, and I'm just going to be left with 5 squared k plus 3. And since we know that the set of integers is closed under addition and multiplication, this is also belonging to our set of integers, so I can call it a new k value. For example, I can call it, for example, k1, right? So I have that 5 to the 2 m plus 1 minus 1 is also divisible by 8 because I've found an integer, k1, such that 8 times that integer is equal to this expression, which I'm testing for divisibility by 8 by. So if that is the case, that means m plus 1 belongs to our set S, and n belonging to S was the thing that implied this thing to be true. And since we already showed that 1 was an element of S, and we have the second assumption, then By the principle of mathematical induction, that means the set of all values for which this identity is true is equal to the set of all natural numbers n. That means that 5 to the 2m minus 1 is divisible by 8 for all natural numbers n. And that completes the proof. The last example that I want to explore today in terms of what mathematical induction can be used to prove is an inequality problem. So we've already shown that it can be used for divisibility, equality, and now we have inequality. So we have three different realms for which mathematical induction can sort of help us in terms of proving statements. So our goal is going to be to prove that some natural number is always strictly less than 2 to the power of that natural number for all natural numbers n. And once we get to single variable calculus and the study of limits, this identity has actually become very, very useful there. So if you want to pause this video and try and prove this on your own, feel free to do so. So let's start off by formally defining our set. So let S be the set of all natural numbers n such that n is less than 2 to the power of m. Now, if you get tired of writing this formal statement, you can say that S is defined to be equal to the set of all n such that n is less than 2m with n in the set of natural numbers. That would be a set equivalence way of writing that formal statement if you want to avoid, for example, the English wording of that all. So the first thing that we need to see is, does 1 belong to the set? So 1, is that less than 2 to the power of 1? So that's implying that 1 is less than 2, and we already know that that is true. So that means 1 belongs to the set S. So what we're going to do now is we're going to assume that m belongs to the set S, which means we're going to assume that n is less than 2 to the power of m, where n is a natural number. So the question that we need to answer is m plus 1 also an element of S? As usual, this is usually the harder part, but for this proof it's actually not that difficult. So what do we have? So we know that n is less than 2 to the power of m. By the properties of real numbers, this also means that m plus 1 is less than 2 to the n plus 1. That is, we've added 1 to both sides of this expression. So keep in mind that's what we want on the left-hand side for this thing we're trying to prove. So that's a good first step. And what is this going to be equal to? So we know that 1 is less than 2. So that means 2 to the n plus 1 is less than 2 to the n plus 2. Right? So from here, what we have, keep in mind, 2 to the first is less than 2 squared because 2 is less than 4. We know 2 squared is less than 2 cubed because 4 is less than 8. So we can say that this is just 2 to the power of 0 to the power of 1, 2 to the power of 2. That should be a plus sign. And we continue this all the way down to 2 to the n plus 2 to the n, where n is some natural number n. And you, in some sense, could prove this with mathematical induction, too. So notice that up to this point, we have that m plus 1 is less than 2 to the n plus 2 to the n. Keep in mind, those are just the same exact objects added together. So object plus object equals 2 of those objects. So we have that m plus 1 is less than 2 of those objects. So by properties of exponents, we can just add those exponents together. So 1 plus n is just m plus 1. So we have that m plus 1 is less than 2 to the m plus 1, which is the identity that we're trying to prove. So we have proven that m plus 1 belongs to our set S, which means by the principle of mathematical induction, we have that S and n are identically the same exact sets. So this means, in concluding, n is less than 2 to the n for all n in the set of natural numbers. So we've shown that mathematical induction can be used for equality proofs, inequality proofs, and divisibility proofs, and there are several other things for which we'll get into later. But that's just an introduction to this mathematical foundational proof method, mathematical induction. Hope you enjoyed this video, and I'll see you in the next one. Take care.